about terminal and non-terminal alkynes. Terminal alkynes are those in which triply bonded carbon, that is at one end of the chain. Acetylene also is terminal alkyne having two end carbons which are triply bonded. In this compound, which is 1, 2, 3, 4, but2-ine. This is number 1, 2, 3 and 4. Triple bond is at number 2 carbon. This is but2-ine, which is not an end carbon. Hence this is known as internal alkyne. This is example of internal alkyne, but2 but2-ine. Now coming to methods of preparation of alkynes. One method is dehydrohalogenation of dihalides. Dihalides are compounds having two halogen atoms in them, and in these one halogen from this carbon and hydrogen from this carbon gets removed by treating it with alcoholic KOH, as a result of which C2C triple bond is obtained. Potassium halide plus water are also formed. In next step, this haloalkene containing halogen and one C2C double bond in it, this is treated with sodamide NaNH2. This is a stronger base in comparison to KOH. KOH in second step cannot remove HX from this haloalkene to give alkyne. Some stronger base is required. NaNH2 can solve the purpose. Here, by applying this NaNH2, X from this carbon and H from adjacent carbon, they are removed and alkyne is formed. Sodium and ammonia are formed in this process. Next method, second method, that is dehalogenation of tetrahalides. Tetrahalide 1,1,2,2. This is 1, 2, first carbon. This also contains two halogen atoms, and on second carbon also two halogens are there. Hence it is known as 1,1,2,2 tetrahalide. This is treated with zinc metal. Zinc removes two halogens, X2, 2 zinc, take up 4 halogens, and formation of 2ZnX2 is there, along with formation of alkyne molecule. An above method, dehydrohalogenation of dihalides, this 2 halogen containing compound can be 1,2-dihalide, 1,2-dihalide like this. On adjacent carbons halogens are there. These are also known as vicinal dihalides. 1,1-dihalide means geminal halide, dihalide can also be taken. These two were methods of formation of alkynes in general. Some special methods are there for formation of acetylene, that is ethine. One method is action of water on calcium carbide. CaC2 is calcium carbide. When it is treated with 2 moles of water, calcium hydroxide CaOH twice is formed as byproduct with the formation of acetylene. 2 carbons here, 2 hydrogen from here, and 2 OH ions. They combine with calcium to give calcium hydroxide. Acetylene is formed. Second method is by dehalogenation of haloform. Haloforms are compounds with formula CHX3. If X is chlorine, it will be chloroform. X is bromine, it will be bromoform. X is iodine, then it is iodoform. Here, for example, iodoform is taken. 2 moles of iodoform, 1, another molecule of iodoform. When treated with silver, 6 moles of silver. 6 Ag take up 6 iodine atoms to form 6 AgI, and 2 carbons of iodoform get triply bonded to give acetylene. Third method of formation of acetylene, when methane is treated with oxygen at very high temperature, 1773 Kelvin, acetylene is formed along with formation of carbon monoxide and hydrogen. This method used for industrial formation of acetylene, means on large scale acetylene is produced by this method, by controlled oxidation of methane. Fourth method is Kolbe's electrolytic reaction. In electrolysis, one electrolyte is taken in a tank, electrolytic tank, and 2 electrodes, anode and cathode. These are immersed, and electric current is passed through this. When the electrolyte dissociate into ions, cation and anion, and these ions move towards respective electrode. Positive ions will migrate towards negative electrode, and negative ions, anions, will move toward positive electrode. This process is called electrolysis. Here the electrolyte taken is sodium or potassium salt of malic acid. Malic acid is CHCOOH double bond CHCOOH, and its potassium salt is CHCOOK double bond CHCOOK. Solution of potassium salt of malic acid is taken in the electrolytic cell. Electrolysis is carried when acetylene is produced at anode. As we can see, at anode, these anions will move towards anode, and cations, potassium ions, will move toward cathode. Water is also taken. Here solution of this was taken. Water was also present. It also dissociates to give H positive and OH negative ions. H positive cations, they also move towards cathode. At anode, these malate ions were there. Malate ions lose their charge on its electrode anode. CH-COO double bond CHCO is formed, which is unstable one. Unstable, and this loses two molecules of carbon dioxide to form acetylene. At cathode, potassium ion and hydrogen ion both are there. Hydrogen ion from water and potassium ion from potassium salt of malic acid. H ion has greater discharge potential than potassium ion. So H ion, two H ion take up two electrons to give hydrogen gas. In the tank, potassium ions are there. Also, from the dissociation of water, hydroxide ion were there, and the solution KOH is there in the tank, making it alkaline. That's all with method of preparation of acetylene. Higher alkynes can be prepared from ethyne and other lower terminal alkynes. For this, any lower alkyne with formula RC triple bond CH that is treated with sodamide NaNH2 in presence of liquid ammonia, which will give sodium salt of lower alkyne. Ammonia will be evolved here. This sodium salt of lower alkyne reacts with alkyl halide. This is nucleophilic attack of acetylide ion on alkyl halide via S2 mechanism, furnishing higher alkyne in which H has been substituted by R dash. So higher alkyne with formula RC triple bond Cr dash is formed along with formation of sodium halide. So higher alkynes can be prepared from lower terminal alkynes. Terminal alkyne means the end carbon is triply bonded. Only then the H of this terminal carbon will be substituted by sodium, and as a result it will be attacking on alkyl halide. It will act as nucleophile, and SN2 substitution will take place in giving higher alkyne. That's all.